Okay, so we're going to discuss work in this video. In a typical high school physics class, typically you calculate work by force times distance. But that only really works if every piece of the force, the weight of an object, is traveling in the same distance, and if the force is constant. So if you have a solid object and you're moving it a fixed distance, that's great. But that's not always true. And so what we want to look at is a couple of examples where we have to use calculus, we have to integrate because either the distance is changing for each unit of force or the force itself is changing as we move. Now, the basic premise of the integral is to treat dx like our distance, and then we integrate force dx, or we have some differential expression for the force for each unit of distance that it gets moved. But the integral will then supply that either that sort of extra dimension, so to speak. Now, we're going to start in this video and look at a couple of simpler examples involving springs and sort of gravity type problems, lots of simplifying assumptions. In another video, we'll look at chain problems. And then in another video, I'll also look at the tank problems, which I personally think are the most complicated. But let's start with the simpler cases and look at the spring problems. Spring problems are usually given in terms of Hooke's law, which is the force itself is equal to kx, where k is a constant that depends on the spring, and x is the distance from its natural length. So this is important because sometimes these problems will give you the total length of the spring, and you have to make adjustments based on how that equilibrium value is expressed. So sometimes they will say, we're going to stretch it 6 inches or 6 centimeters beyond its initial length. And in other cases, they'll say the spring is 1 meter long and we're stretching it to, 1.2 meters or something like that. So you have to make these adjustments based on the way the problem is worded. But let's look at a particular example and see how this is set up. Now, in this case, the question says that it takes 16 pounds of force to stretch a spring 6 inches. Yes, sometimes you have to deal with English units and not SI units. How much work is done stretching the spring 6 more inches? Now, it is very common to convert inches into feet for these problems. It will change the value at the end if you don't convert from inches to feet. But if you work solely in inches, as long as you're not involving gravity or anything like that, then it's not necessarily that the answer is wrong, but you do have to be careful about what units the answer is expressing, what it's expecting in terms of foot pounds or inch pounds or what have you, because those units are going to matter. So, but here it's typical to convert to feet. So 6 inches is a half a foot because 6 divided by 12 is 1/2. And then if I plug in my x equals a half and set that equal to my force, I can solve for k. Again, this is very common in spring problems involving work. I get in this case that the force is 32 times x, where x is in feet, and F is in pounds. If we want to pull it 6 more inches, then we are pulling it from 6 inches to 12 inches. And so we're going to integrate from 1/2 foot to 1 whole foot. And so we integrate the force from the starting point to the stopping point over the distance. And so we're integrating from 1/2 to 1. Our force we found was 32x. And when we integrate that, we get 16x squared. We plug in our limits and we end up with 12 foot-pounds. Now, if we were to integrate in inches, our constant would be different and our integral would go from 6 to 12. And what we would end up with is 144 inch-pounds, which you can see if you convert your feet to inches, you will get the equivalent expression, but the units will be different. So again, it's important to keep that unit information in mind. Now, it's also worth noting that sometimes these problems will be expressed in terms of a weight applied. If a weight is applied, you will need to use gravity to convert to feet or to a weight, a force type problem in order to do this. Particularly if you're given SI units, they may give you the mass, and then you have to use gravity to convert that to a force in order to calculate the constant for Hooke's law. Another thing to keep in mind is that some textbooks will give you nonlinear functions for the spring force, in which case you may not have to find the constant at all. All right, now let's look at another example, but this time involving gravity. Now, these propulsion problems are somewhat similar to the idea of Hooke's law, particularly in most textbooks that use them. We're ignoring lots of things that could theoretically go into this problem. We're ignoring the fact that technically, as you launch a rocket into space, that you burn fuel, and so the mass of the rocket decreases. For these, I mean, this is a calculus problem and not a physics class, so we ignore that. We ignore things like air resistance. If you're in a sort of more traditional calculus-based physics class, particularly if you're in a sophomore level situation, they will probably have you develop a much more complex scenario that takes more factors into account. But in a calculus class, we're just sort of looking at how do we set this up structurally, and then you make modifications in physics. So here we're just going to use our force is equal to the gravitational constant times the first mass times second mass over distance squared. Now, the only thing that we worry about so much in the calculus course is that we're going to assume that all of these masses and constants are remaining constant. So the gravitational constant is a constant. The mass of the Earth is certainly more or less substantially constant. The only thing that could potentially be changing is the mass of the rocket. But to make our calculations simpler, we're going to assume that that is also roughly constant. And in that scenario, we can reduce all of our constants basically to force is equal to some constant over x squared. Now, what's important about this is that you should not, in most of these problems, you're not expected to go look up the gravitational constant and the mass of the Earth and estimate the value of the mass of the rocket when it's fully fueled. Instead, they're going to tell you something in the problem, typically about how much the rocket weighs or something like that, so that you can calculate the force that's being applied at a particular point, typically on the Earth's surface. And that will give you the information you need to find the constant for this particular scenario, similar to the Hooke's law example. And then you run through the integration. Now, one difference that you do have to account for is the fact that when you launch a rocket, you are launching it from the surface of the Earth, and the distance is measured from the center of gravity, which is not the surface of the Earth, it's at the center of the Earth. So you're not starting from zero, you're starting from the surface of the Earth. And again, to make these problems simpler, typically calculus books, although not all of them, but typically they will set the radius of the Earth to be some nice round number to make the numbers a little bit easier to manage, rather than using, I think the radius of the Earth is closer to 3,960 miles instead of 4,000 miles. But again, to make the numbers work out, typically they will say you can approximate the Earth radius as this. Again, the setup is generally similar. The only issue is how the force is measured. Again, in SI units, they will tend to give you a mass, which you then need to use gravity to convert to a force, to a weight. Whereas in the English units problems, they will tend to give you the weight or the force, and then you can directly use the formula in order to calculate your constant. So let's look at our example. We want to send a rocket into orbit 1,000 miles above the Earth. The rocket weighs 5 tons at launch. This is what the information we need to get our constant, and then calculate the work done getting it into orbit, neglecting air resistance and fuel spent. So here is our force formula. We're told that it's 5 tons, so I'm going to use tons as my base unit for force rather than pounds. If you want to use pounds, remember that pounds is 2,000 pounds per ton. So I set 5 equal to K over 4,000 squared. And again, 4,000 because it's launching from the surface of the Earth, not from the center of the Earth. So at 4,000 miles distance, it has this weight. And then we end up with a very large number typically for this kind of problem. The gravitational constant itself is very small, but the mass of the Earth is very large. And so you end up typically with a very large constant for this kind of a problem. And then we're going to integrate from where it's launched, which is the surface of the Earth, to its orbit, which is 1,000 miles above the Earth. And then this is our force, and we integrate dx. And we end up with our integral from x to the -2 becoming -1 over x. And this negative, in fact, is what helps us get a positive number in the end, because when we plug in the upper limit, 5,000 miles above the center of the Earth at a radius of 5,000 miles, that is going to be a smaller number than 1 over 4,000. And so when we do the subtraction, we end up with, in this case, 4,000 mile tons after we have done all the arithmetic. Again, miles because we're measuring distance in miles, and tons because we left the force unit in tons. And of course, if you have to rescale to feet or to pounds, then you would simply rescale this value in the same way that you would rescale the linear unit. Okay, so the one other thing that I wanted to mention based on this example is that in some textbooks, they will also include Coulomb's law problems where you're calculating the force between 2 particles. And Coulomb's law looks very similar to the gravitational constant law, but it uses a different constant, obviously, and it uses the charges of the particles Q1 and Q2 instead of the masses, but it functionally works the same way. So as long as you can express your distance as a linear distance with just one variable, then you can set up your Coulomb's law problems if you encounter them in a calculus book, basically the same way. You don't have to worry about all the specific constants. You use a particular initial scenario to find the constant that you need for your specific case. And then as the distance increases or decreases, you can calculate the work done in pulling the charges apart or in pushing them together. But fundamentally, those kinds of problems, again, they don't appear in every book, but when they do appear, they're very similar to these gravity problems. Okay, next video, we'll do chains.